Unit 5 review. Outcome. I can factor a quadratic expression using a method of my choosing. Refer back to section 5.1.1 for more examples over this one. We're going to factor 7x squared minus 34x minus 5. We're going to factor this one using the box method. This is coefficient A, coefficient B, and coefficient C. A times C is 7 times negative 5, which is negative 35. And B is negative 34. We want to find two numbers that multiply to negative 35 and they subtract to give you negative 34. If you're not sure which factors they are right away, list them out in a T-chart. We'll write the factors of 35. We have 1 times 35, 2 doesn't work, 3 doesn't work, 4 doesn't work, they're all decimals, and then 5 times 7. 6 also doesn't work. And so we know we're done listing the factors because the next integer after 6 is 7. We've already used that. Since this is a negative 35, one of these two factors has to be negative. Since our result is a negative number, the bigger number needs to be negative. So the factors that we want to use is negative 35 and positive 1. Once we get here, we're ready to set up our box. In the first box, we're going to write 7x squared. In the last box, we're going to write negative 5. That is from the leading term and the constant term. Now, these two boxes will be those two factors that we found followed by x's. Minus 35x and plus 1x. And if we have negative 35x plus 1x, that gives you negative 34x. We're just decomposing that middle term. From here, we will factor out the greatest common factor of each row and each column. If we look at this first row, the GCF of 7 and 35 is 7, and they both share an x, so we're going to put 7x here. The GCF of the first column is x. If we multiply x times 7x, we do get 7x squared. If we look at the second row, the GCF for this one would be a 1. And the GCF of the last column would be a minus 5. And if we multiply the rows and the columns together, we should get each of those four products again. We have our factors, x minus 5 and 7x plus 1. It's our factored form of this expression. Outcome. I can factor an expression using the factor by grouping method. This is also in section 5.1.1. We'll factor x squared minus 16x plus 64. A times C is 64, our B is negative 16. Find two numbers that multiply to 64 and they add to negative 16. Negative 8 times negative 8 is a positive 64, and negative 8 plus negative 8 is a negative 16. Again, if you didn't see that right away, you can list out your factors. Now we can rewrite this. X squared, and instead of negative 16x, we're going to put minus 8x minus 8x, and then plus 64. So we get these from our factors. From here, we'll group them. We put the first two terms in parentheses, the last two terms in parentheses, and a plus sign in the middle. We'll take out the GCF of each grouping. The GCF of x squared and minus 8x is x. Inside, we're left with x minus 8. Because if you divide each of these by x, this is what's left over. On the next one, we could take out a negative 8. And we're left with x minus 8 again. Divide each of these by negative 8 to get those results. Now, notice they both have an x minus 8. We could factor that out of each of these terms. So we have x minus 8 factored out, and then we're left with x minus 8 on the inside. Now we have the same factor repeated twice. So that is the same thing as x minus 8 squared. And this is our factored form of this standard expression. Outcome. I can factor an expression using difference of squares. This is from sections 5.1.1 and 5.1.2. We want to factor 25x squared minus 9. Let's recall the difference of squares formula. We have a squared minus b squared equals parentheses a plus b times a minus b. Let's determine what a and b are. We know a squared is going to be 25x squared, and b squared is 9. If we take the square roots, we get a equals 5x and b equals plus or minus 3. We'll plug those into the difference of squares formula to get our factors. 5x plus 3 times 5x minus 3. That's our factored form. You could also factor this using the other two methods from the previous examples. We'll just say that for ax squared plus bx plus c, in this case, this b would equal 0. We are doing that process. Outcome. I can use completing the square with quadratic equations and expressions. This is from sections 5.3.1 and 5.3.2. What should be added to complete the square of 2x squared minus 5x? First, we will factor out the 2. So then we have 2 parentheses x squared minus 5 over 2x plus something. To get this something, we're going to square our negative b over 2. So if this is b, then we're going to input 5 over 2 times 2 squared, which is 25 over 16. Finally, we'll multiply that 2 back in to each of those terms. It says 2x squared minus 5x, and then the 2 and the 16, it would become a 1 over 8. So what we want to add to this blank to complete the square would be 25 over 8. Outcome. I can convert between standard form and vertex form for a quadratic equation. Refer back to sections 5.2.2 and 5.3.1. What is the vertex form equation of f of x equals 2x squared minus 8x plus 6? Let's refer to the vertex formula. We have negative b over 2a for our h value, and then for our k value, you plug that answer into the formula. Also known as c minus b squared over 4a. All right, let's identify our a, our b, and our c. And then we'll plug those in. Negative 8 over 2 times 2. 8 over 4 gives you 2. That's your h value. And then to get your k value, just plug that into the formula. So we're plugging this 2 right here and right here. We'll evaluate that. We have 4 times 2, 8 minus 16 plus 6. Negative 2. Next, we'll rewrite this in vertex form. F of x equals 2 parentheses x minus 2 squared minus 2. Where this a is from right here, we have the h right here, but it has a negative sign, so you change the sign. And then the k is this minus 2 right here. Outcome. I can apply vertical and horizontal translations to a quadratic function. Refer back to 5.3.1 for these. Where the transformations from f of x equals x squared to g of x equals parentheses x minus 3 squared plus 5. If we were to sketch a graph, the parent function would be in the middle right here, and then our new function would look something like that. The transformations are right 3 and up 5. If you can't remember the properties about left versus right, consider making a table of values and plotting the points, like this. You might be wondering which x values to plug in here. You want to definitely plug in the x value that makes this 0, and then just 1 or 2 other points that are around that number. Outcome. I can apply reflections and dilations to a quadratic function. Sections 5.3.1. Where the transformations from f of x equals x squared to g of x equals negative 7 over 5 x squared. This minus right here makes it reflect across the x-axis. And then the 7 over 5 is getting bigger from the 1 right here. So that is going to be a vertical stretch by 7 over 5. Here are the properties from your pre-reading for these transformations. If you can't remember these while you're taking the exam, consider drawing a table of values for x and y and sketching a graph with them. Outcome. I could calculate the discriminant of a quadratic equation. Refer to section 5.2.1 for more of these examples. What is the discriminant of 5x squared minus 4x plus 1? Let's recall the discriminant formula. B squared minus 4 times A times C. First, identify the coefficients A, B, and C. A is 5, B is negative 4, and C is 1. We'll plug that into the formula. Negative 4 squared minus 4 times 5 times 1. 16 minus 20 is negative 4. We have a negative number. That means we're going to have two imaginary solutions. And that would go in for the next one. For I can explain the relationship between the discriminant and the types of zeros of quadratic function. Refer to these three from your pre-reading. If the discriminant is greater than 0, there are two unique real solutions. If the discriminant is equal to 0, you have one repeated real solution. And if the discriminant is less than 0, you have two complex imaginary solutions. Outcome. I could find the equation of a quadratic function given its key features such as vertex, axis of symmetry, and intercepts. Refer back to section 5.3.1 for these. Write an equation of a quadratic in vertex form that has a vertex of 5, 7, opens downward, and contains the point 0, 2. We're going to use all of this information to solve for A. For the vertex, we're going to plug the 5 in for H, the 7 in for K, the 0 for X, and the 2 for Y. Opens downwards means that A is going to be negative, and it's going to be opening this way. Let's plug in these values to solve for the A. 2 equals A parentheses 0 minus 5 squared plus 7. Negative 5 times negative 5 is 25. Let's subtract the 7 from each side. And divide by 25 on each side. This can reduce to negative 1 over 5. A equals negative 1/5. This is what we're most interested in finding. Once we found the A, we can write out our vertex form equation. Y equals negative 1/5 parentheses x minus 5 squared plus 7. Notice that our vertex form equation, the x and the y become variables again. You replace the a with your found number, and then the vertex numbers are still plugged in for h and k. Outcome. I could describe the characteristics of a quadratic function given its equation. Refer back to 5.3.1 for these. Write an equation of a quadratic in factored form that has x-intercepts negative 6, 0, and 8, 0, and the y-intercept 0, negative 96. Just like the previous example, we want to solve for a. We're going to plug these in. The negative 6 is going to be plugged in for R1, the 8 for R2, this 0 for x, and this negative 96 for y. Or use those to solve for a. Negative 96 equals a parentheses 0 plus 6 times 0 minus 8. When they give you the x-intercepts, we write your factors. Those r values will have the opposite signs as what is given, just like the h has the opposite sign for the vertex. We have negative 96 equals negative 48a. Let's divide each side by negative 48. A will equal 2. Once we found our a, we just need to plug everything back in and revert the x's and y's back to variables, and then we have our answer. Y equals 2 parentheses x plus 6 times x minus 8. And this is our factored form equation. Outcome. I could graph a quadratic function given its equation. Refer back to section 5.3.1. Sketch a graph of the function f of x equals x plus 4 squared minus 1. It has a positive a value, so it's going to open upward. The vertex h, k, it would be the opposite of the inside, so negative 4, and then comma, negative 1. For the zeros, we want to set the equation equal to 0 and solve for the x's. Add 1. Get the square root of each side. You have plus or minus 1 equals x plus 4. So you have two possibilities. You have negative 1 equals x plus 4 or 1 equals x plus 4. Subtract 4. Negative 5 equals x and negative 3 equals x. Those are your two zeros. And then to get the y-intercept, we'll plug in 0 for x and evaluate it. That's 15. So your y-intercept is 0, 15. After we've found those characteristics, it is now easy to draw a sketch of the graph. It's opening upward, and let's go ahead and plot our vertex. It's like right here, that's your vertex. Your zeros at -5 and at -3. And then your y-intercept. And then just draw a quadratic that goes through those points. The rest of it doesn't have to look perfect. You just want to make sure you plot those 4 key points. Outcome. I can find the zeros of a quadratic equation when they are real. Refer back to section 5.4.1. Solve the following equation using the quadratic formula. X squared plus 9x plus 3 equals 0. The first thing you want to make sure is that it's in standard form, where you have something x squared plus something x plus a constant equals 0. We already have that, so we'll go to the next step. Identify your coefficients. A equals 1. There's only one x squared there. B is 9, and C is 3. From there, we'll plug it into the quadratic formula. All right, we have x equals -9 plus or minus the square root of 81 minus 12 all over 2. Okay, 81 minus 12. 69 is 3 times 23. Those are both prime numbers and they're not perfect squares. So we have our solutions. X equals -9 plus the square root of 69 over 2, or x equals -9 minus the square root of 69 over 2. When it has plus or minus, it just means that there's 2 different solutions. One where you add those terms together and one where you subtract them. Outcome. I can solve conceptual questions related to the locus definition of a parabola. Refer back to 5.2.1 for this one. Draw a diagram illustrating this. A parabola is the locus of points P such that FP equals DP, where F is the focus and D is the directrix. So we'll draw a parabola. It could be facing any way you want. I'll go ahead and have it facing upward. We have the focus and we have the line, the directrix. From here, we have a line going from the vertex to the focus. This is FP. And then we have another line from P to D. DP and FP are the same distance. This is the focal length. Outcome. I can explain the relationships between the coefficients in standard form equation of a quadratic and the features of its parabola. Refer back to section 5.3.1. How can you determine the following about a parabola in terms of a, b, and c in the equation y equals ax squared plus bx plus c? If you have a positive a, that is going to be opening upwards. If you have a negative a, it's going to be opening downwards. The vertex, the h value is negative b over 2 times a, and then the k value, you plug in that result into the formula. And then the y-intercept will be 0, comma, whatever the c value is. Outcome, I could calculate the focal length of a parabola. Refer back to section 5.2.2. What is the focal length of the function f of x equals 1/8 times x plus 4 squared? The focal length formula is 1 over 4 times a. In this case, a is 1/8. Sometimes they refer to focal length as p or c prime. Let's plug this in. We have 1 over 1/2. So 1/2 goes into 1 2 times. Your focal length is 2. Outcome. I can model and solve real-world application problems involving quadratic equations. Refer back to section 5.4.1. A ball is thrown with an initial height of 3 meters and has an initial velocity of 10 meters per second. When does the ball hit the ground? The leading coefficient is negative 9.8 meters per second squared. Here's our position formula. H of t equals 1/2 a t squared plus VLT plus the initial height. So this is acceleration. This is initial velocity. And then this is the initial height. And then the t is the time. And this is the current height. Using our givens, we're going to plug these into the formula. H of t equals negative 9.8 t squared plus our initial velocity 10t, plus 3 for our initial height. We want to know when the ball hits the ground. If this was a non-calculator question, they would either have you stop at setting up the formula, it would be something that's easily factorable, or they would have you set it up with the quadratic formula and then stop from there. For this problem, let's go ahead and graph it using a calculator. So if it asks for the maximum height, you would use this number, the 5.55. If it wanted to know what time it was at its maximum height, you would use the x value, 0.5102. But in this case, it wants to know when it hits the ground. It's at that 1.26 number. And it's in seconds. And let's go ahead and sketch a graph of what we had on Desmos. And we get these numbers.